Good morning. All right, I'm going to talk through this synthesis, last two syntheses from Friday, and then we're going to do some NMRs today. So for this one here, I'm going to kind of walk through all the different possibilities you could do and talk about issues you'd have with them. So looking at this, we have an alkyl group here, we have an acyl group, and we have a chlorine, which means there are three different possibilities we could do for our first step. So let's just kind of throw each of them on there. So if we chlorinate, adding in Cl2, Al, Cl3. We can put chlorine on this position. Acylating, so throwing in our acyl chloride. Gets us to here, and then alkylating. We'll put us here. So taking a look at all these, we have chlorine, it's a group 4, it's an orthopara director. So that would let it alkylate on the correct, or you could put things into the correct spots. We have this acyl group here, this is a meta director. We need to put something here, so that makes sense. And we have this alkyl one, which is also an orthopara director, it's group 3. Like so. So let's start with this alkyl one. If we were to chlorinate, which is really our only open position here, put a chlorine here. Chlorine is a group 4. This is a group 3. So this is still going to be our higher priority. So at this point, we're not going to have the ability to add something here. So this pathway isn't going to work. All right. These other two here, we want to probably alkylate both of them. So both the alkyl and the acyl groups are pretty big. So if you put the acyl group in with this here, it's most likely to add para as well as the alkyl group. For meta, it doesn't really matter. It only has one option. So throwing in AlCl3 would get us a little rough. These two pathways here. Now for this first one, we have the same problem as we did above. This is group 3. This is a group 4. So it's going to be orthopara to this group 3, which again is not the positions we want to add to. We want to add to this meta. So this one isn't going to work again. And we're left with just this one here. So if we take this, we throw in Cl2, AlCl3. This is a group 3. This is a group 5. This is sp3. It's pretty bulky. This one's only sp2. It's a little less bulky. Most likely we're going to end up adding this para position. These two orthos are pretty blocked. then we're able to get our desired product in this one. So usually these are just a matter of putting things in the correct order. All right, our next one is a little bit more variable. I'm going to go through one pathway, but there's actually quite a few you could do. There we go. So our synthesis was for this compound here. We had a Br, Cl, and a nitro group on this. Nitro, we're going to have to go through some sort of diazonium. Intermediate to make this. I'm going to start off by doing bromination first. You could also do a nitrosylation first, and I'll go over that in a second, but let's do the bromination first. So we throw in Br2 and FeBr3. We could brominate. Adding a nitro. Nitros are pretty big. They're most likely going to want to add para. So HNO3, H2SO4. Can get us to this product here. From this point, you're going to want to chlorinate and then reduce. And I'll talk about why in a second. So if I throw in Cl2, AlCl3, my Br is a group 4, an orthopara versus this NO2, which is a group 5, maybe group 6. I think it's actually group 6. So orthopara positions are going to be these two. Our para is blocked, so we'll be able to chlorinate. Here, followed by going through our diazonium pathway. So adding in zinc, HCl, and heat lets us reduce this nitro down to an amine. We can add in NaNO2 and HCl. To make our diazonium, and then copper nitrate, CuCN, will let us replace this diazonium with a nitro group, or okay, and then so the question in the 930 was, can you reduce this first before adding in the Cl? So if we were to try to do that, draw that out in pink. If I was to add zinc, HCl, and heat here, I'm going to run into an issue. This is now a group 1 versus a group 4, which means if I try to chlorinate at this point, I'm going to end up chlorinating at these 2 positions, which is going to give me the wrong product. So again, order of operations is pretty important for these. Going to determine if you can make your correct product or not. Okay. The other question was, could you nitrosylate first? So throwing in HNO3 H2SO4. Let's you add your NO2. You've got an orthopara director, or sorry, a meta director. You need a chlorine in your meta position, so you could chlorinate. From here, we also want a bromine. So our chloro is our group 4. It's going to be an orthopara. Taking a look at our molecule, the 2 bottom positions are pretty blocked. This ortho is most likely what you're going to add to if you threw in Br2. And then from here, you're just going to do the same thing. So this pathway also works. So you could throw in your zinc HCl to make the amine, and then go through your diazonium pathway. And you could also do it this way. So there's usually a couple of different ways to do these. As long as it works and it makes sense, it's fine to have a different pathway than what I originally drew. All right. So take a look at some NMRs. I'm going to start off with the NMR packet that we did around chapter 1. So this is, it's going to be under files, practice problems, and exam 1. There's an NMR worksheet there that really doesn't look good. If you're looking to grab this one. So we never went over these last 3 problems. We did this NMR worksheet, so I'm going to do them today. And then a couple extra ones that I loaded up in the lecture notes section. So anything from 6.5 to 8 is going to be an aromatic ring. And for this class, that's going to be benzene. So benzene normally has, like just regular benzene has 6 H's on it. Each of these positions are sp2, so they can each hold 1 hydrogen. So when we have something like this, where we have 5 H's, we're going to have 1 open spot. So this peak here, this is not like, I know someone asked why this is all accounts for one thing. It's a mess of a bunch of different peaks that just kind of got slammed together. And that's why you're seeing this all merged as one 5H peak. They could also draw out a bunch of different peaks, and as long as they all add up to 5H, it's also going to be this kind of configuration here. All right, so from here, the other thing we have to consider is the ppm for things that are attached to our ring. So if we think of a ketone, this H here, which is in the 2 to 3 range, it's one position away from a double bond. It happens to be a double bond of an oxygen. If I have an H that is benzoic to my ring here, it's also one position away from a double bond, one of the double bonds from an aromatic ring. This is also going to show up in the 2 to 3 range. So looking at this here, we have one peak in the 2 to 3 range. It's a singlet, it's a 3H, so it's probably a CH3. This is going to be toluene here. All right, looking at a more complicated one. Still doing 5H. We'll get into 4H in a minute. We've got an aromatic ring. We've got one peak in the 2 to 3 range. The CH. The CH has 6 peaks. This is 5, 2, 3. All right, so it's in the 2 to 3 range. It's most likely the one that's connected to a ring. It's a CH. Supposed to have 5 neighboring H's. It currently has 0. So it needs a CH3 and a CH2 in order to make 5. Our CH2 is supposed to have 4, currently has 1, so it needs a CH3. For labeling these, I don't expect you to discern between the aromatic ones, so these are all going to be A. B is going to be our CH. C is going to be our CH2. D is our CH3 with 1 neighbor. So this CH3 is next to the CH. And then this CH3 is next to the CH2. So it should be the other one. So the ones with 5 H's should be pretty straightforward. When you have 4 H's, when it starts to get more complicated. So I'm going to put this down for a second, talk through some different possibilities. So there's 4 different things you can have when you have, or 3 different things you can have when you have 4H. All right, so as you may have guessed, they can either be ortho, meta, or para to each other. The para is going to be really nice because you have them on either side. It is a symmetrical molecule. These two peaks here are going to give the same signal. You're going to get something in your 6.5 to 8 range. And it's going to look like two doublets. They're both going to be worth 2H. If I pull the last NMR from that worksheet, you can see two nice doublets here. They're both worth 2H. That's going to be a para confirmation. Meta is going to be, it is detectable sometimes, but often not. So this H in the middle here is by itself. The closest neighbor here doesn't have a proton on it. The closest neighbor over here doesn't have a proton on it. This should be a singlet. This one has one neighbor. It should give us a doublet. This one has two neighbors. It should give us a triplet. This one has one neighbor. It should give us a doublet. And this is what it would look like. You'd have a singlet, two doublets, and a triplet here. This is very optimistic though. A lot of times they get smushed and you might get something that looks like this, where it's just a whole bunch of peaks on top of each other. You can't tell which one it is. Also, sometimes the doublet and the triplet merge together, or sorry, the doublet and the singlet merge together and they make what looks like a triplet, but they're actually these two smushed on top of each other. So it's a bit of a mess whether or not you have this or if you have this. And a lot of the times you're just going to have to write out both of them. So for this one here, our perfect world situation, this has one neighbor, should give you a doublet. This has two neighbors, should give you a triplet. Two neighbors, triplet, doublet, and you get something that looks like this. Again, often you're going to get this. So when you have this, you're going to have to write out the product for both of them, like both the ortho and the para one. So I'll do that for the next example. And we'll kind of talk through these. So let's take a look at this one. We kind of have a mess. It's 4H, there's a total of 4 protons here. It's a little hard to tell. We have, this one is a triplet if you really zoom in on it, which I'll zoom in a little bit, but not that much because it's still hard to tell with this screen viewer. We have kind of a mess here. This is one where we're not going to be able to tell if we have the ortho or the meta product. So we're going to have to draw both of them. Okay, so taking a look at everything else, we have 2 peaks in 2 to 3 range. They're both attached to our ring. One has 3 neighbors, 0 neighbors, 2 neighbors. I'm going to start by just drawing out the ortho one, and then we'll draw out the meta one second. So we're ortho one. Putting a CH2 on one of my positions. a CH3 on the other one. That leaves me with one open spot here, which would be this other CH3. My other possible product is the same thing. I'm just going to have to shift where that other CH3 is down to the meta position. You only need to label one of them. So if you're doing this on an exam, I'm going to mark this as A. Again, I don't need you to tell me which one is which because that's going to be really difficult. B is going to be our CH2. C is going to be our CH3 attached to the ring because it has 0 neighbors. D is going to be the one attached to this CH2 here. So for this one, you'd end up with 2 different products. All right. Same thing for this one here. This is a mess. I can't tell what it is. Maybe that's a singlet, maybe it's not. Maybe it's part of a triplet. We're just going to count this as having to be both of them. Besides that, we're going to do this like normal. So I'm going to start by just drawing the ortho one, and then the para ones, or the meta ones, the same thing, just shifting down one of the groups. So I'm between 6.5 and 8. I know it's an aromatic range. Got 2 open spots because it's a total of 4 protons here. Got 2 signals in 2 to 3 range. They should both be attached to my ring. CH3 is terminal, so I don't have to do anything with that one. Our CH has 6 neighboring protons, so that should be our remaining 2 CH3s here. This could also be the meta version of this. Ooh, man, that's a little rough. I'll redraw the meta over here, just as like lines. So putting our labeling on here, this is A, B, C, D. A is all of our aromatic ones. C is just going to be the CH3 that's attached to the ring. B is our CH. And D is our 2 symmetrical CH3s. All right, last one of these is our nice para example. We have 2 doublets here. This is a para configuration. So we can start with that. Looking at our molecule, we have a chlorine in here. We've got a peak between 4 and 5, peak between 2 and 3. So our 2 and 3 is most likely on our ring. So normally a peak for chlorine or any halogen, this H is between 2 or 3 and 4. We're attached to our benzene ring, it's between 2 and 3. If it's attached to both, it's going to compound. So normally between 3 and 4, but also plus 2 and 3, this could end up pushing this all the way to the 4 to 5 range. If you think of like a normal carbon as being between 1 and 2, our 2 to 3 range is 1 above that, or 3 to 4 would be 2 above that. So having both of them pushes it to 3 above that, which would be this 4 to 5 range. Taking a look at our actual structure, we have this 4 to 5 range CH. So this CH is attached to our ring, and our Cl supposed to have 3 neighbors, so that would be the CH3. All right, put some labels on it: A, B, C, D here. A going to be the aromatic protons. B is our CH, C is our CH3, and D would be our last CH3 down here. All right, so I'm going to move on to the other worksheet. So this one is under files, lecture notes. Should be something like aromatic NMRs. This is actually the exact same one we just did. I realized that during the last class, or not, that we just did, that we did at the beginning for the 5H one. So I'll go through this real fast. It's a 5H, which means it only has one open spot. We've got, this is 6, 5, 2, 3 here. Between 2 and 3 is attached to a ring, so that would be our CH. It's got 5 neighbors, which should be a CH3 and a CH2. CH3 is terminal, CH2 has one open spot. Supposed to have 4 neighbors, currently has 1, so it needs a CH3. And because we already did this one, I'm not going to go through and label each of these. Let's talk about this next one. Okay, so we have actually a discernible thing here. So this is a triplet, a doublet, a triplet, and a doublet here. And if this was an exam, I would tell you what those are because it's a little tough to see this one here. But taking a look at these, this is actually going to give us just this configuration. We're able to determine which one it is. If we look back to our nice little ideal situation diagrams, we're supposed to have doublet, triplet, triplet, doublet, which is what we have for this one. So for this one, we can actually rule out the meta. We've got oxygen, what looks like an OH, a CH2, and a CH3 here. So our CH2 is, they're both singlets. This one's between 4 and 5. This one's between 2 and 3. So 2 and 3 is on our ring. 4 and 5 is probably on our ring and the OH. So putting those together should get us to a final product here. A, B, C, D. So A is going to be all these protons. B is our OH. C is our CH2. D is our CH3. Already B there, should be D. All right, I'm gonna give you a little bit of time to go through the next two of them on your guys' zone, and then we will talk through them together. And I'll write out some peaks for you guys. Fifteen. All right, so for this top one here, we've got a mess. We're not gonna be able to tell which one it is. I'm gonna draw the ortho product first and then draw the meta second. We've got two symmetrical CH2s, two symmetrical CH3s. They're both connected to CH2s, so these are probably gonna be linked together. This was the ortho product. Would look something like this. Our CH2s are in the 2 to 3 range, so they're gonna be connected to our ring. Our meta product same concept, just spaced out one more. Labeling these. A is going to be our aromatic protons. B is going to be our CH2s. C is going to be our CH3s. All right, our bottom one here is a little bit nicer looking. This is our para. It's got the nice para spacing. We just have two doublets. We have a CL. We have a peak between 2 and 3, a peak between 4 and 5. So 2 and 3 is most likely to be attached to our ring. Supposed to have 3 neighbors, so that would be a CH3. 4 and 5 is most likely attached to both our ring and the CL, the CH. Supposed to have 2 neighbors, so that would be a CH3. Our other CH2 is supposed to have 4 neighbors, currently has 1, so we need another CH2 on the other side. We have our aromatic protons. E and F here are going to be indistinguishable. They're both triplets. They're both CH3s. They're in the 1 range. So starting off with A, it's going to be our aromatic protons. B is going to be our CH that's directly attached to our ring. C is our CH2 directly attached to our ring. D is our other CH2. And then E and F are going to be both of these CH3s. All right, that is aromatic NMRs. We're not going to do triple substitution or anything like that for these. So on Wednesday, I'm going to start on chapter 19. We'll see how far we get on that before our exam. So Friday will be the last day of new material. So I will see you guys on Wednesday. Have a good Monday.